My name is Dr. Jenny Barnes. I am a college tutor at Queen's College. We're a lovely college, very friendly, please apply. I also do access and outreach work within the physics department. So the outline of my talk is I'll give some general comments about the PAT. I know you've just had a session all about admissions. I'll talk a bit about the format of the PAT as we have it now. And how you might prepare for the PAT. We do realise it's a slightly difficult thing, so some advice which is also on a leaflet that was out the front, things like the past papers and the syllabus, a bit about what we're looking for, some past paper questions I thought we might go through because you've all come to do physics, you want to do some maths this time of day, and then maybe some other resources that you could find that would also be useful. So if you apply to Oxford for physics, physics and philosophy, material science or engineering science, you must take the PAT. The PAT is hard. If everybody got 100% on our test, it would be no use. So less than 1% of the students get between 90 and 100 marks. So do not be discouraged if you see hard questions. That is what to expect. You should, however, develop a strategy. Guys, do you need to find somewhere? There are some seats over there. You need to develop a strategy on how to tackle the paper. Are you going to try some questions first and then come back to others later? Are you just going to start at question 1 and work through to the end? You do need to have a bit of a strategy. The format of the PAT is it is 2 hours long. It is a mixture of maths, which is 50 marks, and physics, which is 50 marks. The rubric, the actual layout of the paper has changed over the last 12 years. If you look at the past papers, some had multiple choice, some didn't have multiple choice. The current format is that there are 6 maths multiple choice questions. Each of the questions is worth 2 marks. There are 6 physics multiple choice questions, and each of those is worth 2 marks. And then there is a selection of higher mark questions on physics and maths. The marks could range between 3 marks and 10 marks, but the questions are mixed up. So you might get a maths question followed by a physics question, and then another physics question, and then a maths question. This is mainly because people used to do the maths and not get onto the physics. It is a physics test. We would like you to do some physics questions. That's why we've mixed the questions up. Now, we asked our current students in physics, engineering and material science, how did they prepare for the PAT? And these are their top tips. The most useful thing they said they did was some past papers. And I will mention where you can find those on our website. It is important to check the syllabus. We do publish the syllabus. We try and cover first year maths and first year A-level physics, but it's important that you check, because some schools might teach things in different orders. It's quite useful to do some other problem-solving type questions, things like physics Olympiad questions or Isaac physics questions, because these are a bit more like the kind of questions that we set on the PAT rather than just do lots of A-level questions. That probably will not prepare you very well. It's also important to do some questions under timed conditions. When we asked the students what was the most difficult thing about the test, then quite a lot of them said it was timing. You've got a lot of things to do in 2 hours, so it's really important that you plan your time well. The style of questions is also there, a bit different to A-level questions, and so that can also be a little confusing for some people. What was interesting to us when we did this survey was that over 35% of the people who replied did all the work themselves. So it is not true that you have to be doing some huge amount of support from your school in order to succeed. Only 25% of the people who replied to us had a regular PAT preparation club in their school. So a lot of people perhaps just asked their teacher 1 or 2 things, asked them, maybe they just had 1 session. Some of them only had help from a maths teacher, not from a physics teacher. So, you can do the work yourself and you can succeed, okay? Could I just ask the 2 people at the back, unfortunately we have no standing in the lecture when the lecture is running. There probably are some seats over that side. Thank you very much. Okay, so some past papers. Past papers are available online on our website. So this is our current past paper page. When you look at it, it's very difficult to read, but it says paper and it says report. For every year, there is a report, and the report will give you the mark needed to get an interview that year in physics. Okay, a lot of what I'm talking about is applicable to physics. Engineering and material science use the PAT in a slightly different way. They combine it with what you've said on your UCAS form, because it's very important that you do understand what material science and engineering are. Physics, we kind of hope you understand what physics is. The mark that is chosen each year as the sort of, you have to get this mark to get an interview, that is chosen so that the number that we interview is constant. So it does mean that there's not like a pass mark. The number will vary. So if the paper was very hard, you might need to get 50 marks to get an interview. If it was quite easy, you might need to get 60 or 65. But you have to check each year. And really, you're comparing yourself against a very able cohort who have applied to study physics. So on the 2017 paper, last year the average was 52 plus or minus 14, and everyone who scored 59 and above was offered an interview. That's again in physics or physics and philosophy. We had 87 people who did not achieve that, but we were also invited for interviews, so we had a total of about 530. And so 500 to 530 is about what we interview every year. So this is how we select what the cutoff point is. And all this information, I don't know it because I work here, I know it because I found it in the report. Okay, so there is information in the report that can be useful. So, past papers. One thing which people do often ask us about is solutions. I'd like some solutions to the past paper. There is only one set of solutions which is on our website. This is for the 2009 paper. We know that solutions do exist on the internet. They are out there. They are not our solutions. We haven't gone and checked that they are correct, but we're hoping that they will agree with our solutions. The reason we don't publish our solutions is that if you answer the question correctly by any method, you would get the marks. We don't want you to think that there is only one way to do a question. If you come up with a solution which is totally different to everybody else, but it is correct, you get the correct answer, that is fine. Okay? So the people who mark it are physicists and engineers and material science. They do understand the material, and they will be able to spot what is a correct solution and a non-correct solution. It's important to write down your working because this might give you some marks. So, I know your teachers probably always tell you write down your working. It really is important you do write down your working. The syllabus, we try to cover first year maths and first year physics A-level. It is worth having a look at it and doing some preparation this summer while you don't have, your final year exams to worry about. If you haven't covered the material now, ask your teachers, because it is possible they might cover it in September. So it's worth having a conversation with them now. We do not offer a formula sheet, but we do let you use non-graphical calculators this year. Okay, so again, as Armin said in the previous lecture, something which is just very basic, very simple, so that you don't waste time because you can't multiply two numbers together. That's the reason we're allowing calculators. This is probably almost impossible to read, but is the syllabus. It is on our website. It may look longer than it has before. It was updated on the 6th of June. And what we've done is we've just tried to more clearly lay out the syllabus. So it's more obvious the different topics. The syllabus itself has not got longer, okay? Because the physics one especially does look like it's got really long, but actually what we've tried to do is to include a bit more information. So for instance, there was one which said, we expect you to know about the solar system, and that was a bit vague, so we've changed it to basic knowledge of bodies in our solar system, including planets, moons, comets, and asteroids. Name and relative position of the planets should be known, but detailed knowledge of their physical parameters is not required. So we need you to know that there are things called planets, that they have names, they are in a certain order, but we don't expect you to know what a Jovian day is or how many moons Saturn has. Okay? So that's the kind of how we've expanded the syllabus, just to try and give a bit more detail so it's a bit clearer what we need you to know. Okay, so with the test, what are we looking for? We're looking for whether you can do the basics, whether you can think about the answer you've got. So we might, a question might talk you through with a certain set of parameters and then say, and suppose we change the wavelength of light we shine on this sample, how would that change? Can you use new information that we've given you? So it might be that we introduce something you've never seen, you never likely to have seen, but we try and put all the information in the question, and it's how quickly can you pick that up and use it, because that's the skill that we need when people come on the course. And can you express a question in terms of mathematical expressions, because it's really important that you can put things in terms of maths. That's what physics is. So I thought it'd be useful to go through some past PAT questions. So if there are any parents in the room, you may get a little bored, but feel free to join in at this point. These questions are all from the 2006 question paper, okay? So these particular questions were some maths. So this one is really a test of can you do the basics. So we'd like you to sketch the functions sine squared x and 1 over x squared minus 1. So I will give you a few minutes to have a go at that. Okay, so for the first one, where we have y equals sine squared of x, so I can think of at least two different ways I could do this. I could possibly differentiate it, find turning points, but that seems a little bit complicated. What I'd probably do is I might sketch sine of x, so y equals sine of x. I would, of course, remember that sine of x is 0 at x equals 0. I would remember that sine of x is 0 at 180 degrees, and it's 0 at 360 degrees, and it basically does standard sine wave. it goes between 1 and minus 1. And so in order to find the square of that, well, I know I'm always going to get a positive number now. I'm not going to get, so none of this quadrant is going to be negative anymore. The zeros would still be the same. They're not going to change. So 180 would be 0, 360 would be 0, and 0. But now I'm only going to go, instead of the range being 1 to minus 1, it would be 1 to 0. So at 90 degrees, that's still going to be 1. At 270, it's no longer going to be minus 1, it'll be 1. I'm expecting a smooth function, so I would join the dots. Is that what people have got? Yeah? Okay. All right. So the second one, y equals 1 over x squared minus 1. Might need to clean the board. So again, with this one, I could potentially do some calculus. I could find turning points. But I could also look at some other graphs and perhaps do some translations of it, and that would be helpful. So if I said, what would y equal x squared be? That would just be that graph. If I said y equals x squared minus 1, y, the whole graph will shift down. That point would be minus 1. And then I want the inverse of that. So that means that wherever previously I had a 0, that's now going to be a vertical asymptote. So that's 1 and minus 1. This region is all going to be positive, so this one's got to be positive. This region has got to be negative. And this region on the right would have to be positive. Okay. If I do 1 over minus 1, I would get minus 1. But now as I've got numbers between 0 and minus 1, they're all going to be getting more and more negative. In this case, as x becomes very, very minus infinity, then y would be becoming very large. So I'm going to be getting 1 over a very large number is a very small number. Okay, so that's how I might work it out, but you might work it out a different way, and you might say, okay, I'll differentiate that, I'll find turning points. Okay? But curve sketching is a common thing that we set on the PAT. It's also a common thing for interviews. So it's really useful that you know how to sketch graphs, and you have a strategy for sketching graphs. Okay, so that's a nice warm-up question. Right, this one is a bit harder. Okay, this is the area of a shape. In the figure below, the radius of the larger circle is twice that of the smaller circle. Find an expression for the fraction of the area of the square which is occupied by the two circles. I warn you now, the answer is not just simple integers. Okay? So I'll give you a few minutes to think about how you might tackle this problem. Okay, so this is quite a tricky question. The question gives you no letters or numbers or anything to start with. So this is a sort of example of a question where we want you to take a question and turn it into some mathematical expression. So there are multiple ways of doing this. The way I'm going to go through is to say the important thing is to think what's along the diagonal. Okay? So the radius of the large circle is twice the radius of the small one. So I'm going to call the radius of the small one r. So the radius of the other one is 2r. The length of the square I'll call a. You can call it any letter you want. You can call it x if you like. And so what I'm looking for is I'm looking for the area of the two circles divided by the area of the square. So the area of the two circles, that's quite easy to work out. So area of the circles would be pi r squared for the smaller one, and then pi 2r all squared, which would be 5 pi r squared. We can all do that? We can all remember the formula? Okay. Right, the area of the square, that will just be a squared. So writing down that might get you a mark or two. Okay, that would be useful. But what we now need to do is to try and get a in terms of r, or get r in terms of a, but try and eliminate them, try and combine them. So on our diagram, if we look along this diagonal, the length of that diagonal, where should I put it? There, would be root 2 of a. It's a along here, it's a along there, so that's 2a squared must equal this length, so this length must be root 2a. Are we all agreed with that? Okay. But we also know, if we split this up into a section of 4, this length here must be 2r. That's the radius of the circle. This length here must be r. That's the radius of the smaller circle. So this triangular part here, we know that this length is 2r, because that's the radius, and that's 2r. So that means that this length is 2 root 2r, because this is a triangle, so that's 2r, that's 2r, so we can work out the length. Similarly, those are both r, so this one is root 2r. So that means that the length of the diagonal of the square, which is root 2a, should equal 2 root 2r plus 2r plus r plus root 2r. So that's adding up the 4 segments of that line, which is r. I think there's 3. 1 plus root 2. Okay, so this means we can now relate a to r. So the fraction that we want, which is 5 pi r squared over a squared, that's 5 pi r squared over, so a would be 3r over root 2, 1 plus root 2 all squared, which should hopefully come out to be 10 pi r squared over 9r squared 1 plus root 2 all squared. The r squareds will cancel, and you get 10 pi over 9, 1 plus root 2 squared. Okay? Now that's not a number you'd probably see in an A-level exam, would you? But you might, but possibly not. Okay? So that's what we kind of mean by this is slightly harder than your standard A-level question. But doing the geometry, trying to work things out, you know, partial marks could be given. Okay? Have I got the answer right? Are we okay with that? Okay. Right. Okay, let's do some physics. You're here to do physics, okay? So this was a multiple choice question that year. So I can do show of hands for this one. A block of niobium, a metal with density 8,570 kilograms per meter cubed, has sides of length 3 centimeters, 4 centimeters, and 5 centimeters. What is the maximum pressure that can be exerted by this block when it is stood upright on one of its faces? Okay, so this is a multiple choice question. You don't get long. Okay, so you've had a couple of minutes. That would be as long as you'd want to spend on this question. So can I have a show of hands of those of you who think the answer is A, 4.3 kilopascals? Some, okay. B, 430 pascals? Some. C, 2.6 kilopascals? No, oh, one person at the back, okay. D, 510 kilopascals? Another one at the back. Okay, the answer is actually A. Okay, so this one of the things which questions will often try and catch you out are things like, have you converted the units? Did you notice that things were in centimeters, but the density was in per meter cubed? You are lucky that I saw some of you with calculators. When people sat this paper, they weren't allowed calculators. Okay. But yes, the answer for that one is A. Okay. So the side that it should be is the 3 by 4 centimeter side. The smallest area is what you needed. Why is it A? Okay. All right. So pressure equals force over area. Are we all happy with that one? The force in this case would be mg. So we have to work out the mass. So the mass is equal to the density times the volume. So that's the 8,570 times 0.03, 0.04 times 0.05. Okay, so that would give you the mass. And the area would be 0.03 times 0.04. Okay. So it's always going to be the smallest area would exert the greatest force. the maximum pressure. Are we happy with that? Okay, this is another multiple choice question. A Martian attempts to measure his mass using a set of bathroom scales in his house on Mars and gets a reading of 93 kilograms. Unfortunately, his scales were designed for use on Venus. Given that the gravitational strengths at the surface of Mars and Venus are 3.8 newtons per kilogram and 8.8 newtons per kilogram respectively, what is his true mass? Okay, we'll do a show of hands again. Hands up if you think the answer is A, 40 kilograms. Very popular on the back row. Okay. Answer B, 106 kilograms. Nope. Answer C, 215 kilograms. That one's more popular. And D, 245. The answer is indeed C, 215. This is because you need to take the 93 kilograms, multiply it by the 8.8 and divide it by 3.8. Okay? Because the 8.8 is Venus, the 3.8 is Mars. Right, the last question I was going to go through is this one. This is lots of circuits. I know how much students like circuits, okay? Right, so this one, there's a bit of words to this question. The diagram below shows a circuit in which a bulb lights up with normal brightness, okay? So you are expected to know what the symbols in that circuit diagram mean. In the circuits below, the bulbs and cells all have the same specification as the bulb and cells shown above. Determine whether the bulbs marked by the letters in these circuits are brighter than normal, normal, dimmer than normal, or off. So there were 8 marks for this because there are 8 different bulbs, okay? So the first circuit, there's just one bulb A that you have to come up with, B for the second circuit, okay? So you're going to need a little table that says whether you think things are brighter than normal, normal, or dimmer than normal, or off. Okay, so let's start filling our table in. So for bulb A, hands up if you think it's brighter. Normal brightness. Dimmer. Yeah, dimmer. Go for dimmer. Okay, what about B? Is that one brighter? Normal? Yeah. Right, good. You understand this? Right, okay. So for C, brighter, normal, dimmer, off. No, it's actually the same. It's actually normal brightness. If you look at the circuit, there are 2 cells in it. So although there are 2 bulbs, if you look around the main outside loop, there are 2 bulbs, but there are 2 cells. So it's actually normal brightness. Okay, D, is that brighter? Normal? Possibly. Dimmer? Off? It is indeed off. The reason it's off is because there's no potential difference across it. Therefore, no current can flow. Okay, so that one is off. E. What was E? E is there. Okay. So is that brighter? Normal? Dimmer? Off? It is dimmer. Okay. F. Is that brighter? Normal? Dimmer? No, it is normal. It is normal, that one. Okay. Right, G. Okay, is G brighter? A few say brighter. Normal? A few normal, some dimmer. Off. The brighter ones were correct because you've actually got 2 cells. If you look at the outside loop, you've got 2 cells on 1 bulb. So that one must be brighter. So what about H? Is that brighter? Normal? It is actually normal. That one is normal brightness, okay? So there were 1 mark for each of those questions. So the reason this one is normal is because you've got 2 cells and 2 bulbs, okay? Okay. Right, I think I will move on to some other resources. So on the sheet, which is outside, there are some useful websites and resources. The British Physics Olympiad, they have some very nice questions, again, which are problem-solving type questions. They do have solutions to all of their questions, okay? So that might be helpful. I want to study engineering. You don't have to be interested in engineering to use this website. It is useful, even if you're applying to do physics, because the questions on there are sort of maths, you know, they're just maths questions and physics-y questions, so they're absolutely fine. There is also Isaac Physics. If you've never come across it before, there are some postcards outside about Isaac Physics. It's a website which is specifically designed to improve your problem-solving skills. And what I've done is I've collected together a few questions which looked to me like the sort of questions you would find on the PAT. So if you go to that web address, which I don't think it's on the leaflet, then those are questions which, you know, are of a suitable standard. Okay, so the sort of level of Isaac Physics questions, you get different levels of them. You want to be looking for like level 4, level 5 is the sort of real kind of pushing the mathematical nature of the PAT. But we will also have some questions which might be about level 2, level 3 as well. Okay, so that's just a selection of maths and physics questions. But there are many, many more questions on Isaac Physics which would be applicable to the PAT. So to conclude, to prepare for the PAT, we would suggest you practice with some past papers. Do check the syllabus and make sure you've covered things or you've looked at material for them. And use some other resources, not just A-level questions. That's really important. Don't expect to get it all right. I'm sure a lot of you here have never scored less than 90% in an exam ever. That's not this kind of exam, okay? If you try and make sure you get to the end and you have a go at all of the questions, that will be the best advice, okay? Thank you very much.